All right, so today's lesson, we are starting chapter 8. So it's our first lesson in chapter 8, and we're going to come up with new equations of a line. So in grade 9, we learned y equals mx plus b, and the standard equation for a line ax plus by plus c equals 0. But now we're going to come up with vector and parametric equations of a line. And this is important to come up with equations for lines in 3 dimensions, because we can't use y equals mx plus b to write an equation for a line in 3 dimensions. So I'll go over the introductions later. I want to start with a little investigation to sort of recall how we would write a y equals mx plus b and how we're going to come up with something new. So here I have a line, right there. The equation is y equals 1/2 x plus 5. So just a reminder, number 5 is your y-intercept there, and 1/2 is the slope of the line. So what we're going to do, it says draw a vector that is parallel to the line. Okay, so I'm going to put it at the origin. Don't have to, but I'm going to. And draw one that is parallel to the line. So something like this. The length doesn't matter. All right, there's a vector parallel to the line. And label it M. I'm going to label it M. Okay. Now, how many possible vectors M exist that are parallel to this line? Well, infinite, right? There'd only be one that goes through the origin, but you could draw it anywhere you want. There's an infinite number of vectors. And, well, actually, there would be more going through the origin because I said the length doesn't matter. So if we change the length, then we can have different vectors that go through the origin as well. All right, the next step says to draw a position vector starting at the origin. So we have the tail at the origin and the tip on the line. It doesn't really say where on the line. I can do anywhere. I guess if you just have any known point, like there, then we can draw it to that point. And we're going to label that vector R0. And that'll be a position vector to any known point on the line. And how many possible ones are those? Well, there's an infinite number of points on the line. As long as you know what they are, you can draw a position vector to that point. All right, next says in the equation y equals mx plus b, we know the slope is m, and m changes the orientation of the line, the slope of the line. And b is your y-intercept, that changes the position of the line. So what about M and R0? How do those affect them? Well, notice if I change this vector, let's call it our direction vector, right, then essentially I am changing the slope of the line. So this is very analogous to the slope. And what about the position vector R? Well, again, I'm changing the position, whereas B changes where it goes through the y-axis. R, I'm changing where the position of some point on the line actually is. So we can actually use these then to define any point on the line, or to write an equation for that line, as an equation for a line defines all the points on the line. So next, number 4 says draw the vector A, -1 and 2. So these you can't see, but this is -2, -4. So they go up by 2's. So -1 and 2 would go to about there. So that's our vector A. Now compare this vector with the equation of the line. Well, it certainly looks like it's perpendicular. And notice if we were to analyze the slope, well, this slope is the negative reciprocal of this. So the slope of our line here is 1/2. And the slope of this is -2. And if you remember from grade 9, your negative reciprocal shows that you have something perpendicular. So in this case, A is perpendicular to M. All right, so let's look at the new grid. So this time they gave us our equation of the line in standard form, and I've drawn it here. And we need to draw the vector B, 3, and 4. So that would be about from the origin to about there. Again, this vector B does look to be perpendicular to the line. In fact, it is. If you were to rearrange this equation, you would see the slope is negative 3 over 4, and this slope is 4 over 3, rise over run. So they are perpendicular, but the interesting thing is, if we look at it, the coefficient for the x in standard form is our x-coordinate for this position vector. Similarly, the coefficient in front of y in standard form is our y-coordinate. So that's an interesting comparison to make that could come in useful later on. Right, so let's look how we're going to combine all this. This is what we're going to do. So imagine we have this line here, okay, L. What we can do is we have our direction vector m and a position vector r naught to any known point on the line, And then if you simply take, we can translate m over here so that we're adding r naught to m, and we can change the length of m however we want by just adding some scalar multiple, in this case t, where t is any real value. And if we do that, it changes the length of m, and then the sum of r naught and tm will point to what we call r, pointing to any point p x of y on the line. So we can use that to write our vector equation. R, which points to any point on the line, equals a position vector to a known point on the line plus a scalar multiple of our direction vector. And now we can actually split this up into what we call parametric equations. So if we only have a two-dimensional line, then you can think of r as being a point xy on the line. R naught is some known point, x naught, y naught. And our direction vector is some values a and b. So what we can do is say x, match all of our x coordinates. So x equals x naught plus t times a. So there's our first equation. Then y equals y naught plus t times b. So there's our second equation. And if we had this in 3 dimensions, we can write a third equation for z, which would look like this. So this is what our equation, our vector equations and parametric equation for a line would be, which we can use in either 2 dimensions or 3 dimensions. So let's come down here and try some examples with this. So example number 1. Determine the vector equation and parametric equations of a line passing through this point with direction vector m. Well, if it passes through this point, then what we can say is the vector OA, which goes from the origin to that point, can be our position vector to a known point on the line, which is then just 1 and 4. So then we can write our vector equation r as our position vector to a known point plus some scalar multiple, let's say t, times by the direction vector m, which is -3 and 3. Now the direction vector, we don't really have to use -3 and 3. We can use any scalar multiple of that, and it might even be easier, just like when you put a fraction in simplest form, to do the same thing with our direction vector. We can have it by some scalar multiple s and write it as -1 and 1. Where in this case all we did was factor out a common factor, which would be 3. And so in this example, s would be equal to 3 times t. Okay, but this is certainly a much simpler form to write the equation in. And then we can write our parametric equations where x equals our x-coordinate 1 for our known vector plus s times -1, which would be just -s. and our y-coordinate is 4 plus s times 1, which is just s. Now the second question says to sketch the line. I have that down here for us. And determine the coordinates of 4 points on the line. If you're going to determine any point on the line, let's just pick any value for s. And let's take 1 for example. Let's say s equals 1. In that case, our x-coordinate for this point on the line would be 1 minus 1, which is 0, and our y-coordinate would be 4 plus 1, which equals 5. So 1 point on the line is 0 and 5. And you can see I labeled that point right here. If s is 0, you'll get another point. If s is minus 1, you'll get another point. If s is minus 6, for example, you'll get another point. Right? Remember, s can be any real value. You can make s minus 6.2487, and you'll get another point. Right? You have an infinite options there. Next it says, okay, is either q or r on the line? So how do we test that? So let me just move over. Let's test q first. So they say q is minus 21 and 23. All right, so what we're going to do is we're going to plug in our x-coordinate into our parametric equation and solve for s, and then plug in our y-coordinate and solve for s. If this really is a point on the line, the value of s should be the same. If it's not, then it's not a point on the line. Okay, so let's try x. So minus 21 equals 1 minus s. So if we solve that, we will get s equals to 22. Okay, well, what about our y equation? So that's 23 equals 4 plus s. So in this case, s equals 19. So no, this point is not on the line. What's the other point that we needed to test? It was r. So they said, I'm going to do this up here. R is minus 29 and 34. Okay, well, let's start with our x equation here. So we'll plug in minus 29 for x equals 1 minus s. Solving for s, we get s to be 30. Do the same with our y equation. So 34 equals 4 plus s. And if we solve for s, we get s equals to 30. So in that case, we get the same s. So that is a point on the line. Okay, so let's try some example problems now. Our first problem here, number 1, determine the vector and parametric equations for the line containing these 2 points. Okay, well, if we connect those position vectors, we'll realize that our direction vector is equal to those lines where we connect those vectors. And we can solve for that position vector by finding the difference in the coordinates. So our x-coordinate would be 6 minus negative 1. So 6 minus negative 1. And our y-coordinate would be 11 minus 5. And so we get 7 and 6. Okay, if you did it the other way, if you did FE, that would be fine. You would get negative 7 and negative 6. But then again, you can pull out a negative 1 as that scalar multiple, right, to write it in the easiest, simplest form. And then our vector equation, you can pick any of these points. Okay, I'll do minus 1 and 5. That's one known point. Plus some scalar times our direction vector, 7 and 6. Now it's important to note this equation is not unique, because I could have, instead of using minus 1 and 5, I could have used 6 and 11. and that is also an equation for this line. Okay, there's an infinite number of possibilities that you can use. We also need to find the parametric equations. So let's write that. So x equals, so we have minus 1 plus 7s. And y equals, so 5 plus 6s. And again, these equations are not unique. Part B says, what are the coordinates of the point where the line crosses the x-axis? So we're looking for the x-intercept. So the line is going to cross the x-axis at the point A and 0. Remember, where it crosses the x-axis, your y-coordinate will be 0. All right, so if we look at our parametric equations then, we can plug in 0 for y. So we'll get 0 equals 5 plus 6s. Then we can solve for s. So s, rearranging, we get minus 5 over 6. Knowing what the value of s is, we can then figure out what our x-coordinate is. So x equals, using our parametric equation for x, negative 1 plus 7 times s, which is minus 5 over 6. The value of s will be the same for the same point on a line. Right? And evaluating that, we get minus 41 over 6. So our x-coordinate, or our x-intercept, is minus 41 over 6 and 0. Now the last question, part C, says, can this equation also represent the line? So remember I told you this is not a unique equation. So is this another possibility? How can we figure that out? Well, one is that this direction vector, 14 over 3 and 4, must be some scalar multiple of this direction vector. Right? The slopes must be the same, in other words. So 7 and 6. So is there a value of k where that works? And there actually is. Right? If k equals 2/3, right, then 2/3 times 7 gives us 14 over 3, and 2/3 times 6 gives us 4. Okay, so we know that this line is certainly parallel to this line because their direction vectors are the same. Right? But do they lie on top of each other? Are they the same line? So for that to happen, this point here must also exist on this line. So we're going to do what we did before in the previous example on the first page. We're going to test to see if this point exists for our first equation. All right. So first thing we'll do is we'll test for x and for y. So if we do it with x, we get minus 15. So our x-coordinate equals minus 1 plus 7s. Minus 1 plus 7s. And if we solve for s, we get s equals negative 2. Okay, well let's test y, because we should get the same value for s. So we have negative 7 for y equals 5 plus 6s. So 5 plus 6s. And if we solve for s, we get the same negative 2. So yes, this could also be an equation representing the same line. Okay, let's go to our next question. The next question says to determine a vector equation for the line that is perpendicular to this line and passes through the point P. So there's our known point. So what we need to do is find a direction vector for this one. To find a direction vector for this one, let's say our direction vector is AB. Since it's perpendicular to this line, we know that the dot product between this direction vector and this one, minus 3 and 2, must be equal to 0. So if we solve for that, we get an equation minus 3a plus 2b equals 0. Now, again, there's lots of different solutions to that, but the easiest one is just the negative reciprocal. Right? So our new vector m for our equation we're trying to discover here, if we take that as a positive and switch the coordinates, we will get 2 and 3. Does that work in this equation? Well, yeah. If a is 2, we get negative 6. And if b is 3, we get 6. So negative 6 plus 6 equals 0. So that definitely is the solution. Therefore, we know that our new, let's call this R2, for the equation of a line perpendicular to this one is our position vector to a known point, 6, 5, plus some scalar multiple. I'm not going to use s. I'm going to use a different one because it's a different equation, times 2, 3, our direction vector. Okay, where t is an element in the set of all real numbers. All right, last question. This one's a three-dimensional question because we have our x, y, and z coordinates. And it says, determine the vector and parametric equations of the line passing through these 2 points. This is similar, we've done this in 2D. So in 3D, we will simply have our direction vector is going to be equal to PQ, right? Our position vector here. So we need to find the difference in those coordinates. So minus 2, subtract minus 2. That's our x. 3 minus 4. That's our y. And 5 subtract negative 1. And that's our z. So PQ then, or our direction vector, is going to be 0, minus 1, and 6. Therefore, our vector equation of this line, r, equals, choose either point, p or q. I'll just choose p, so minus 2, 3, and 5, plus some scalar multiple of our direction vector, 0, minus 1, and 6. And our parametric equations would be then x equals negative 2 plus 0s, so we don't need to write that. Y equals 3 minus s, and z equals 5 plus 6x. There we go, and that's it.